Good morning, students. There are only 8 who have joined. I was waiting for some more students to join, but I think they are all late risers. Let me start the class for today. In the last lab session, I had come up to this particular point where I discussed inverter circuitry in much larger detail. Today, let me complete the symbol creation and the simulation portion. And if possible, I'll start the next experiment, which is NAND and NOR gate simulation. That is same as inverter only. So I went in much larger detail in this particular experiment so that you will understand all the basics as such. Now, once you pick up these P MOSFET and N MOSFET, once you connect them by means of wires and once you connect the pins and VDD and ground symbols, now what you can do is either we can simulate this directly by giving power supply and the input signals, or else we have an option of creating a symbol for this inverter on our own and use the symbol for testing. We prefer the second method. I think I have told you already. This first one is the circuit diagram, which we will directly convert into layout. We can directly convert into layout. If at all we put the power supply and input pulses here itself, then in the layout, they will not have any counterparts. So it is better that we create one symbol and using the symbol, we perform the simulation. Otherwise also creating symbol is a good method. The reason is, let us say you are going to design one multiplier. If at all you have to design one multiplier, you will have a block level symbol for a multiplier. Inside a multiplier, you will have adders. Inside adders, you will have logic gates. Inside logic gates, you will have MOSFETs. So naturally, MOSFETs are at the lowest level. Using MOSFETs, you will construct XOR gates and AND gates. Using XOR gates and AND gates and OR gates, you will construct adders. Using adders, you will construct multipliers. So that way it is always better that for a logic gate, you will have a symbol. For an adder, you will have a symbol. Finally, for a multiplier, you will have a symbol. These are all high-level symbols. In Cadence, if it is possible, when we construct all these symbols, it is actually possible that we can keep on moving from upper level to lower level or lower level to upper level. That means once you simply double-click on the multiplier symbol and you have a command there. Once you give that command there, it will go down to the adders level. If you choose the adder and go down, you will get into the gate level. Again, you choose the gate and go down, you will come to the MOSFET level. So, as I told you, this is an industry standard tool and all such possibilities are available in the tool. Now, let me proceed further for the construction of the symbols. So, after the schematic entry is finished, a symbol for the design has to be created. For this purpose, click on create and follow the procedure. Click on create and you will have to give cell view from cell view and you can automatically that symbol will come. Symbol pull down menu will come. You will select symbol as a view name and then you will go down. See, it will ask left pins and right pins. Directly from the circuit diagram, it will pick up the pins. If you are given this in as input pin, automatically it will take it as left. And if you have taken the output pin and direction as out, it will take it as right automatically. Now, in your symbol, if at all you want any more other additional pins, you can actually specify here also top pins, bottom pins, even additional left and right pins also you can specify if it is required in the symbol. Otherwise, as it is, you can use it directly. Now, as it is, you can use it, you will get a general box here. The tool does not know that whatever you have done is an inverter. Okay, because this is a custom design. Only you know what you are doing. The tool only knows the connections and the MOSFET's characterization. Otherwise, the tool does not know whatever is the design you are creating. So the tool will simply give you a green box along with the red box. You can see this. The green box is the box. Inside you have in and out and you have a part name. The red box is an outer boundary wherein whenever you pick up the symbol, until this red box, that area is reserved for this symbol. So the tool is going to give you a general purpose box. Now you can delete this green box and you can construct an inverter symbol. Just like in MS Word, you can draw straight lines and circles and geometric shapes. Even in Cadence, you can draw all that now, because Cadence also has got a graphical provision, graphical entry provision. So you can delete this green box and see, just select this. Whenever you select, it will turn into a pink line. Once it turns into a pink line, which means that that particular part is selected. Once it is selected, simply delete and the green box will go away. When the green box goes away, you will have the options of, see, pull down menu, you will have create, shape, line, and create, shape, polygon. All such options are there. Using them, you can create this triangle. This triangle looks really like a lengthy triangle. It is up to you to make it artistic, because it is you who are going to create a symbol. Now you make a triangle. Similarly, you can create shape circle and you can place one circle here. One triangle, one circle, and you can pull this line, outline and the pin together. You can join it there. You can join it this way. Then finally, you can create a selection box and create selection box automatically when red box comes around. Now your inverter symbol is created. Now using this inverter symbol, you are going to create a test circuit now. You are going to create one more cell view called inverter underscore test. And in that, again, you will press I and you go to your library and pick up this inverter symbol. Because you only made a inverter circuit diagram and you only constructed a symbol for that. Now, when you press I from your library, you will pick up this inverter symbol. And again, you will put a wire here at the input, wire at the output, and one output pin. Later on, you will have to select from analog lib, you will have to select V pulse. Let me zoom slightly. From the analog lib, you will have to select V pulse and you have to select symbol. Now at the input, place this V pulse, and in the V pulse, there is voltage 1 and voltage 2. Voltage 1 is 0 volts, voltage 2 in general for all 180 nanometer designs, we select VDD as 1.8 volts. As I told you earlier, you need not give these units. Volt or second, you need not give anywhere. You are directly going to give only the value. But this multiplier you will have to give 20 and small n you will have to give. That yes, you will not have to give, it will automatically come there. Otherwise, let us say you try to give 20n without space. If you give yes, the tool will give error later. Because you can see the tool itself is putting a space between the value and the unit. That is the style of the tool. So you don't have to give units anywhere. Now when you select the V pulse, you give the period as 20 nanoseconds and pulse width as 10 nanoseconds. That means we are selecting a square wave as an input to the inverter. Now, we have selected the V pulse and we have kept it there. Now for the inverter, we need the power supply. Again, for the power supply, from the analog lib, select VDC and give the DC voltage as 1.8 volts. Now, you can see here, I will zoom further. You can see here, you have that supply voltage and we have given the VDD symbol and ground symbol. Because inside the inverter, we already have this VDD symbol and ground symbol. It will relate there. Then to the input, we have given V pulse and we have given 0 to 1.8 volts. You can see the symbol of pulse here. Now this is the input pulse. Once this test circuit is ready, you will have to click on check and save. After saving this test circuit, let me zoom out. So these are all the summary of whatever we have been using. If you press key I in the keyboard, it is for instance, W for wire, P for pin, M is for stretching, Q for property. If at all you want to edit any particular component, let us say transistor's dimension you want to change, you can click on the transistor, you can press Q. It will open up one more window where you can change the properties. R is for rotating, U is for undoing, C is for copying, F is for fit to screen. That means you can zoom out and zoom in and zoom out anytime. When you press F, tool will automatically fit it to the screen. Escape is to exit always. Now our test circuit is ready. Now we have to perform the simulation. So for simulation, we have another tool called Spectre. So what we do is in the test circuits editors window, you have to click on launch ADEL. That is one tool. Analog Design Environment is the tool. So this ADE opens up now. When this ADE opens up, now in that analysis, I'll zoom. Okay. When the ADE opens up, you can see these many analyses are there when you choose the analysis. There is this transient analysis, there is this DC analysis, there is this AC analysis. But we are going to use only these three analyses in our complete lab for this semester. We are not going to go for other analysis. All other analyses are meant for you people to explore, if at all you do any project work here, or else if at all you get into Vlsi industry itself, there you will be making use of many of the other analysis, like see P noise, phase noise analysis, and QP noise, quantization phase noise analysis. That way there are so many such analysis. There is a noise analysis separately. But we are going to use the transient analysis for plotting the waveform. I had told you last time, if x-axis is time, if y-axis is output, then that is transient analysis where you will see the waveform. And if x-axis is input and y-axis is output, that is going to, you are going to see the transfer curve. That is called DC analysis. And if x-axis is frequency and if y-axis is output, then that is frequency versus gain. You are going to see the AC analysis. So in the AC analysis, it is frequency response and gain and bandwidth. Even the phase plot is possible. In the DC analysis, it is the inverter's transfer characteristics, output versus input. Whereas in transient analysis, you are going to see the waveform. So in the inverter, we are not going to use AC analysis because inverter is basically a logic circuit. We will be using only transient analysis and DC analysis. So when you choose transient analysis, give the stop time as 100 nanoseconds because we have given the period of the waveform as 20 nanoseconds, period of the pulse. So we can see about 5 cycles of the input pulse. So stop time as 100 nanoseconds, then click on OK simply. Now again, you will have to choose DC analysis for plotting the transfer curve. So select on DC and click on this save DC operating point. Now you have to click on this select component. You have to double click on this particular button called select component. When you double click on that, you will have to select the input signal now. Whatever is the input pulse, V pulse you are giving, you will have to select that. After selecting that, it will come like this. Select component parameter. You will have to select always the top one, that is DC, VDC, DC voltage. Once you select this, automatically the window gets filled up there. You can see here that component name that is /V0, parameter name is DC. That /V0 is nothing but the V pulse which we have given. You don't have to worry about this V0. That is the instance name which the tool automatically gives to all the power supplies or all to the signal sources when you invoke them. You don't have to give individually component names there. So now you give the start and stop for this pulse because now we want to plot the transfer curve. When you want to plot the transfer curve, we specify the input range from 0 to 1.8 volts. That is start and stop range, that is the sweep range. That is DC analysis. That's all. Then click on OK. Now, you will have both these analysis filled. You will come back to Spectre now. In the Spectre's ADE window, you can see that DC analysis is chosen. T is 0 to 1.8, automatic start stop / V0. And transient analysis chosen 0 to 100 nanoseconds, and the simulation is liberal. Now, after this is done, you will have to select the wires which you want to see the waveform. See, I had told you that at the input you should have one wire, because we cannot select the nodes there. If we select the nodes, the tool will plot the current. If you select the wires, the tool will plot the voltage. So you will have to click on this input wire, then you have to click on this output wire, and the tool will understand that you want to see the waveforms in this wire as well as in this output wire. After that, you simply click on that button. In the ADE window, you have this green button. See, this is play button, this is stop button, just like your DVD player. You have the play button, you have the stop button. Play button is green, stop button is red. When you click on this green button, automatically the tool will plot the waveform and you can see the waveform. Let me zoom out. I hope you can see this now clearly. Okay, let it be. Now you can see the waveform. See, input and output both are plotted. When input is low, output is high. When input is high, output is low. That is easily verified here. And we are seeing 5 cycles of the input signal because we had specified 100 nanoseconds as the simulation time. Now in the DC analysis, we had given the sweep range 0 to 1.8. So the tool has plotted directly a straight line from 0 to 1.8. You can see this. So the x-axis is that input sweep. Now at the y-axis, you can see the output that is coming down. When input was 0, output was 1.8 volts. You already know the working of inverter. Now input is 0, output is 1.8. And when input is 1.8, output has become 0. That means when input was 0, NMOS was off and PMOS was on. And when input becomes 1.8, then the PMOS will be off, NMOS will be on. In between, gradually, in the theory class, whatever is discussed, please recall that this is called region A, this is region B, this is region C, this is region D, this is region E. Let me annotate. So this is now region A. Now this is region B, this is region A, this is region B, and this is region C, and this is region D, and this is region E. This you already studied in the theory class. Let me name it as A, B, this is C, this is D, and this is E. Now, to the responding students, I have questions. Other students are simply watchers or listeners, or I don't know, even they may be sleepers. To the responding students, I have questions. The question is, in region A, PMOS is on, NMOS is off. So obviously, in region A, NMOS is in the cutoff region. Now, PMOS is operating in which region? You know that MOSFET has got 3 regions of operation. 3 regions, that is cutoff, saturation, linear. Now, either you can unmute or you can put it in the chat box. You have to tell me the answer. My question is, in region A, NMOS is in the cutoff region. PMOS is in which region? That is my question.
Linear, sir.
Linear. Okay. Now when we come to region B, now you tell me NMOS is in which region, PMOS is in which region? In region B, NMOS is in saturation region. What about PMOS? PMOS is in linear region. Fine. What about region C? What about region C? Fine. In region C, both are in saturation region. Fine. So in region D now, what happens is PMOS will come to saturation region, NMOS will come to linear region. And in region E, PMOS will come to cutoff region, NMOS will come to linear region. Now relate these terminologies with BJT. When the switch is completely on, in BJT we used to call it as saturation region. And when the switch is completely off, in BJT we used to call it as cutoff region. And when the switch is half on and half off, we used to call it as active region. This was with BJT. In MOSFET, the terminologies are different. In MOSFET, when the switch is completely on, that is called as linear region. When the switch is completely off, that is called as cutoff region. When the switch is half on and half off, that is called as saturation region. So the saturation when we refer with MOSFET is different to that of BJT. In BJT, when we say saturation, it means that the switch is completely on. In MOSFET, when we say saturation, it does not mean that the switch is completely on. The switch is half on. The name saturation is given there because in that particular region, the current across the switch is constant. Even if voltage increases, current will not increase in case of MOSFET. That is why it is working like a current source there. So that is why it is called a saturation region. The scientists who have invented BJT are different. The scientists who have invented MOSFET are different. That is why they have given such names. This is an important point which you will have to remember and understand. Now, we have A, B, C, D, E regions. Now, in which region power consumption of the inverter will be maximum? You will have to tell me. Kuldeep is saying region A. No, it is wrong. Yeah, it is in region C. Can you tell me why? In region C, the power consumption is maximum. Tell me why. V out equals V in. Can you tell a little more in detail?
In region C, both the input curve and output curve get passed through a point.
Yeah, fine. Okay, let me elaborate a little. Harshita is correct here. In region A, only PMOS is on, NMOS is off. So when NMOS is off, current does not flow from VDD to ground. Power consumption is possible only when current goes from VDD to ground, but it will not go. Current only goes from VDD to output. So in region A, there is a minimal power consumption. The power consumption is only because of the load if it is connected at the output. Otherwise, there will be no power consumption at region A. Similarly, at region E, PMOS is off, NMOS is on. So when PMOS is off, no current is coming from VDD at all. Whatever is the output charge, that is going to be discharged to ground by means of NMOS. So in region E, there is no power consumption at all. Now in region C, both are half on. PMOS is also half on, NMOS is also half on. That way, PMOS is working like a very high resistance and NMOS is also working like a very high resistance in region C. In region A, PMOS is completely on. It is a switch. It is completely on, but NMOS is open. In region E, PMOS is completely off. PMOS is open. NMOS is closed. Whereas in region C, both are working in the saturation region, so both are half on. And here is the output. This is where you will have an output. So when both are half on, now you can see VDD to ground, there is a connection now. This is between VDD to ground, there is a connection now. When there is a connection, there is a power consumption here. So we say this as a dynamic power consumption. In the case of a CMOS inverter, there is no static power consumption. In the case of a BJT inverter, there will be static power consumption because at the collector we connect to a resistor. And when the BJT turns on, through the collector resistor, current goes to ground. There is a finite collector current. So in the case of BJT inverter, there will be static power consumption. In the case of CMOS inverter, there will be no static power consumption. This is called as dynamic power consumption, where the power consumption is maximum only at this region C. So, if at all we have to reduce the power consumption to the maximum extent, let us say we don't want to have any power consumption for the inverter, even the dynamic power consumption also we should not have. Then what should we take care at the input side? Can anyone suggest? At region C, we have a maximum power consumption. So there is a transition from region A to B to C to D to E. So at this particular point only, there is a maximum power consumption. Now my question is, if at this point there is a maximum power consumption, it is happening only for some instance. Only for some instance, because we have set this as 10 nanosecond here now, right? This is 10 nanosecond, this is 10 nanosecond, totally 20 nanosecond. So when it is totally high, there is no power consumption. When it is totally low, there is no power consumption. The power consumption is only during the transition. You can see here, only during the transition. When it is going from 1 to 0 or 0 to 1, that is when there is a transition. During the transition, there is this power consumption. Otherwise, either PMOS is on, NMOS is off, or NMOS is on, PMOS is off. Now, if we have to have a reduced power consumption, what can be the measure at the input? Maybe adding gate capacitance at input. No. If we add gate capacitance as input, then the signal shape will be distorted. The square wave pulse will become an integrated wave because capacitor will charge and discharge. So that is not the solution. Anyway, I'll tell you the solution. The solution is rise time and fall time should be as less as possible. Now, this curve corresponds to the rise time, right? Input is rising, at the same time input will be falling later on. Even when the input is falling, that region C will occur here also, at the center here also. So there will be power consumption during the rise time, during the fall time. So if the rise time is minimum, fall time is minimum, then the power consumption of the inverter will be minimum. That is what we have to take care. Ideally, we consider rise time 0, fall time 0, but practically there will be no input pulse which will have a 0 rise time and fall time. We must ensure that our pulses are having faster transitions. Now, the last question in this simulation is, just observe this, I'll zoom this DC transfer curve. Just observe this curve. and tell me at region C, what was supposed to be the theoretical value? See, at region C, what was supposed to be the theoretical value? Exactly at this particular point, what was supposed to be the theoretical value of the voltage? Yes, Kuldeep says this is VDD by 2. It is VDD by 2, means it is 1.8 volts divided by 2. 1.8 divided by 2 is supposed to be 0.9. But you are seeing that it is not 0.9. You can see here, it is not 0.9, it is 0.75. Now tell me, why it is not 0.9? It is supposed to be 0.9 VDD by 2, theoretically. But here, practically, when we do it, it is 0.75. What may be the reason? Any answer? Okay, no answer. Fine. Do you know what is meant by mu n and mu p? Mobility of holes and mobility of electrons. Have you studied it in physics or anywhere else in the theory course?
Yes, sir.
Yeah. Now tell me, I have given you a clue now about the mobility of holes and mobility of electrons. Now you tell me at region C, why is it not VDD by 2? Why is it 0.75? Why is it not 0.9?
Can you repeat your question? I couldn't hear it properly.
Yeah, the question is, in the inverter's transition curve, theoretically, we were supposed to have exactly at region C, we were supposed to have VDD by 2. VDD which we have chosen is 1.8 volts. So exactly at this intersection of the transfer curve, we should have 0.9 volts, 0.9 volts here. At the input when it is 0.9 volts, we want output to be 0.9 volts. But you can see here, when input is at 0.75 volts, output is also at 0.75 volts. Which means the inverter is not switching exactly at VDD by 2. Inverter is switching at less than VDD by 2. That is my question. Now it has relevance with the mu n and mu p, mobility of electrons and mobility of holes. Okay, Harshita says mobility of electrons is more. Fine. Mobility of electrons is nearly 2.2 times than the mobility of holes. For a 180 nanometer VLSI process, the mobility of electrons is nearly 2.2 times more than the mobility of holes. So N region moves from saturation to linear. Fine. That means N MOSFET is faster than P MOSFET. Always N MOSFET is faster than P MOSFET. So when N MOSFET is faster than P MOSFET, you can see transition occurs quickly here. It is less than VDD by 2. Here NMOS will be 2.2 times faster than P MOSFET. Okay. Actually, holes will not move at all. Holes are stationary charges. Electrons have to move to fill the holes there. Only electrons can move. Holes cannot move because holes are the vacancies in the atomic orbits. So electrons have to come from elsewhere, they have to occupy the holes. That is why always the mobility of holes is lesser. In this particular VLSI process, mu n is 2.2 times of mu p. Now, if at all we want to have the practical curve also at 0.9. What can be the solution? If at all we want to have the practical regency point to be at VDD by 2, can we do any design changes?
Increase the P size of the thing.
Okay,
Like
in
increase the
the
mobility.
P MOSFET, increase what? Vanilla is correct. You have to increase the P size. In the P MOSFET, increase which dimension?
Like length or width, that dimension, sir, or what?
Yeah. Whether length or width.
I don't know, sir. I should guess only.
Okay, fine. But do you remember the drain current equation of the MOSFET? IDS equals,
Yes, sir.
yeah, IDS equals mu n into Cox into W by L into VGS minus VT whole squared by 2. That is one equation, right? So drain current equals mu n into Cox into W by L into VGS minus VT whole square by 2. So here, if W increases, drain current increases. So we cannot change L. In general, we don't do any changes with the channel length because channel length is fixed. Channel length we fix it at 180 nanometer here. So now you can increase the W of P MOSFET. If you increase the W of the P MOSFET will become as fast as N MOSFET. So what you can do is, when you physically come to the lab, you remember this particular question and you ask us. I'll tell you how to change the device dimensions in the tool. By pressing Q, you can go to the P MOSFET property and you can change the W. Instead of 2 micrometer, you can increase it. 2 micrometer into 2.2 is 4.4 micrometer. After that, save your design, again plot the curve and see the changes. So that is possible. Okay. Any more questions or shall I proceed further? If there are no more questions, I will proceed to the next experiment, that is NAND gate and NOR gate experiment. Any questions?
No, sir.
Okay, fine. Then let me proceed to the next experiment. If you have understood the inverter experiment fully, then the next experiments are simple. Simple in the sense, in a similar fashion, we are going to plot the, not plotting, we are going to have the NAND gate and NOR gate circuits and we are going to simulate them. Let me stop sharing this PDF and let me start sharing the other lab manual where I have a MS Word file where I can show you the other circuits. Okay, let me start the next experiment. From now on, I'll go a little quickly. Let me zoom. All the procedures remain the same now. I'll only discuss the circuit diagram now. Okay, all the procedures remain the same. Only thing is, two P MOSFETs you will connect in parallel, two N MOS you will connect in series, you will connect ground, you will connect VDD, and you have two options now. You can connect the wire, you can connect the pin directly here called A, and you can join one more wire here. That is one option. Another option is label this wire as A and label this wire as A, label this wire as A, keep the pin here. That is another option. Tool has got multiple options of drawing the circuit diagram. It is up to you. If at all you feel that When you put a pin here, you will have to connect one more line here. If you think that the circuit diagram becomes clumsy, then you can simply label this wire as A, here one more A, and this pin A. The tool is anyhow much intelligent. It remembers all these things. Similarly for B. But I don't prefer this normally. I prefer to put a pin directly and connect a wire here because I will be seeing the connections directly. Otherwise, when we do all this labeling, when we keep the pin separately, later on, we human beings are stupid. Machine is intelligent. We human beings forget. Machine will not forget. When we forget, we only get wrong results there. Machine will give the answers for whatever is your circuit diagram. So I generally prefer putting a pin here and actually connecting a wire there. Because even when you make a layout, you will have to actually connect a wire. In the layout, all these labels will not work there in the physical layout. Anyway, this is one option. And you can see P MOSFET is in N well and N MOSFET is in P sub. So I think you remember all the layers. Bottommost layer is substrate, above which we have well, above which we have diffusion, above which we have oxide, above which we have polysilicon, above which we have metal. In the last class, I spent enough time in discussing this structure. Now you'll have to remember this always. Even if I wake you up from the dream and if I ask you to name these layers, you must be able to name them. Now you can see VDD and ground are metal layers, whereas this gate is polysilicon. Source and drain are diffusion. Okay, then we have this well here. Body is N well. Here the body is P substrate. You will have to remember this. The body of the MOSFET is P substrate. Body of the N MOSFET is P substrate. The body of the P MOSFET is N well. Always keep on visualizing that N well process diagram. Then everything will become clear there. And VDD and ground are always metal lines. And even source and drain, they are diffusion. Now here, from the source, there is the metal connection. Source and drain are basically diffusion. Here also it is diffusion now. Two drains are connected together and it is taken out. That is diffusion. Gate is basically polysilicon. All the gates are polysilicon. In between gate and polysilicon, there is this oxide. Now, I'll zoom this transistor. Just look at this transistor. When you look at this transistor, keep looking at it and keep telling me why it is called as MOS. Why is it called as metal oxide semiconductor, field effect transistor?
That is because the layers are arranged like that, sir. Metal first, then there is an oxide layer between the two, and then the conductor is there.
See, metal is there only for VDD. Otherwise, source is not metal, drain is not metal, it is diffusion. Metal is only there at VDD. Oxide is there between gate and channel. Oxide is not there between source and drain. Okay. The answer is something strange. I know that you will not be knowing this answer, but at least I want to make you curious about the answer. The answer is something strange. Actually, it should be called as POSFET, not MOSFET. Why? The reason is, it is polysilicon oxide semiconductor. See, at the gate there is polysilicon, then there is oxide, then there is this channel. Channel is semiconductor. So it should be called as POSFET. Why are we calling it as MOSFET? The reason is, polysilicon was the recent invention. Before that, they were using the gate material also as metal. Because you have a wire there, right? For gate, you need a wire there. All wires used to be metals only at that time. some 2 to 3 decades before. All the wires used to be metals only. Then they came to understand that the metals will have their own issues, parasitic issues, and the metals will have larger area. Then they invented a process of polysilicon, where we already know that the gate does not need any gate current. That is when they thought gate material can be polysilicon. Wherever we want to take it out of the chip, then we will connect it to a metal and take out a wire outside. Otherwise, inside the chip, it can remain as polysilicon. So initially they had called it as MOSFET because the gate material was metal, then there is oxide, then there is semiconductor. You will have to look at the MOSFET from gate to channel. So earlier they called it as MOSFET. Later on, they changed the gate material into polysilicon. But now we cannot call it as MOSFET. We keep calling it as MOSFET because in the beginning we called it as MOSFET only, the same name is remaining. In Bengaluru, nearly a century before, whatever names British had kept, even today the same names are there. Fraser Town, Cook's Town, Thomas Town, all those towns are there. There was somebody called Fraser somewhere in the previous century. Wherever he stayed, he called his own town as Fraser Town. Even today we call it as Fraser Town. We call this white field as white field. Why it is called white field? Field is not white there. We called it as white field because they called it as white field when white people used to stay in that field nearly a century before. Even now the same name continues. In the same way, in the beginning it was a metal material for the gate, then they called it as metal oxide semiconductor. Now, actually we have to call it as MOSFET. We cannot call it because the MOSFET has been the conventional name. If at all Arvind sir says it has a MOSFET, people will call Arvind sir is a mad fellow. So, let us remain sane, not insane. So, let us keep calling it as MOSFET only. Now, to stop all my unnecessary blabberings, to start with the syllabus once again, the next question now is, let me zoom in a little so that you will see this picture. Okay. Now you know when two P MOSFETs are in parallel to N MOSFETs are in series, this is going to be a NAND gate that you have studied already, right? When A and B are 1, 1, it is both N MOSFETs are on. When both N MOSFETs are on, this will conduct like this. This will conduct like this. At that time, this is 1, 1, both are off. This PMOS is off, NMOS is off. So when both are 1, 1, output is going to be 0. Otherwise, in all other conditions, when it is 0, 0, P MOSFETs are on. Any 1 is 0 also, P MOSFET is on. That way you will get output as 1. So the truth table for this gate is 1, 1, 1, 0. That is the functionality of NAND gate. Okay. Now, instead, if you reverse it, if you make NMOS parallel below and PMOS series above, then it will become a NOR gate. That's all. So you already know the functionality of these gates. You can simply connect these MOSFETs and you can simulate. Now my question is, if at all I connect NMOS in place of PMOS and PMOS in place of NMOS, which type of gate it will be? Wherever PMOS is there in the circuit diagram, I will connect N MOSFET. And wherever NMOS is there in the circuit diagram, I will connect P MOSFET. What will be that circuit? If you want, you can pick up a notebook and you can write it and you can find out the answer.
So PMOS is replaced with NMOS and NMOS with PMOS.
Correct.
That is the question.
Yeah, that is the question.
VDD and ground also swap like that only.
No, 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 no. VDD and ground will remain the same. If you swap VDD and ground, it is simply an upside down circuit. That's all. Any answer?
To find out. Can you give us like 5 minutes more?
Okay, keep thinking. At the end of the class, tell me the answer. Okay, this is one question. If PMOS is replaced with NMOS as it is, and NMOS is replaced with PMOS as it is, what is the output? That is one question. Second question is, can you suggest a circuit diagram for one AND gate now? Because this is now NAND gate. Can we construct a NAND gate similarly? The first question is slightly difficult. You can try it out. Now, can you give the answer for the second question immediately? Can you suggest me a circuit diagram in CMOS for one AND gate?
Put one inverter over there, sir. It become AND gate.
Yeah, that is a very easy answer. But then it will become 6 transistors. If we put inverter, it is going to become AND gate. Oh, I am not in first year. I am your professor. You are in third year. So don't give me such answers.
Sir, easy way is better, no, sir.
Yeah, but it will increase the number of MOSFETs. I want to use only 4 MOSFETs. Just like using 4 MOSFETs, we have NAND gate. Same way, using 4 MOSFETs, can we have AND gate? That is my question.
Is it the way you told earlier, the one you asked us to find out?
Not that. That is not that. CVSL model. Harshita is telling some other complicated thing for me. No. It is not CVSL model. CVSL is having both. That is a different concept altogether. Whatever I am discussing right now is what? Static CMOS. Right now I am discussing the basic CMOS. Kuldeep is telling pass transistor, and Kuldeep is also telling 2 NMOS. 2 NMOS how? Pass transistor is another family. Pass transistor has its own other problems. I am discussing only the static CMOS circuitry. How do we use 2 NMOS? That is my question now. Okay, let me write on my own. I will write a circuit here. I am connecting two Pmos below and I am connecting two Nmos above. That's all. I have connected two Pmos below, two Nmos above. Now 0, 0, these both are off. At that time, these both are on. Pmos are on. So it will conduct this way. Output is 0. 0, 1. 0, 1, upper N MOSFET will be off. Lower N MOSFET, even though it tries to turn on, upper is off. But here 0, 1, one of the PMOS will be on. So it will be 0 again. 1, 0 also same case. 1, 1, both upper NMOS will be on. At that time, because this is 1, 1, both PMOS are 0. So we will get to output 1. So the output here is 0, 0, 0, 1. So now the question is, will this work like an AND gate? That is the question. Harshita is telling the earlier question, if you reverse NMOS and PMOS, we get AND gate. No, no, no. My earlier question was something different. My earlier question was just replace PMOS with NMOS and NMOS with PMOS. That was my question. Here what I have done is I have connected top side NMOS in series, bottom side PMOS in parallel. Now this is one AND gate. And my question is, yeah.
Your question's answer is OR gate, sir, then?
No, no, not that also. My first question is slightly complicated. Okay, is it OR gate? Find out. Anyway,
Sir,
my second question now. Yeah, tell me.
for the second circuit, we'll get output as 0, 0, 0, 1, sir.
Correct. So is this AND gate is my question.
Yeah, sir.
But they don't use AND gate at all. They use always one inverter along with the NAND gate. In CMOS, there is nothing called AND OR. There is only something called NAND, NOR, and inversion. Even in the digital circuitry, when you write Verilog code, later on when you synthesize, even if you get an AND gate, it is always NAND gate in connection with the inverter. Whatever you told earlier is the actual answer. Now my question is, why don't we construct AND gate like this? We are actually not constructing AND gate this way at all. There is a specific reason. Why can't we connect NMOS at the top and PMOS at the bottom? That is a specific question. Why always we should have PMOS only at the top and NMOS at the bottom? Can anyone
Pass
tell
is
me?
strong 1 and strong 0, sir. That is
Exactly, that is the answer. Yes, Kuldeep has given the degraded output is the answer. That is the exact answer. Answer is you cannot use PMOS at the bottom. You cannot use NMOS at the top because at the top you have 1. At the bottom you have 0. PMOS passes good 1. Okay. NMOS passes good 0. Okay. 0 is at the bottom, 1 is at the top because VDD is 1, ground is 0. So always we should have PMOS at the top, NMOS at the bottom. If at all we reverse this, we will get a degraded output. Means if you have 1.8 volts VDD, you will not get 1.8 volts output. It will become maybe 1.4 volts or 1.2 volts. Output will get degraded. That is the reason in static CMOS, we will never have AND gate and OR gate. We will always have NAND gate and NOR gate. Whenever we want AND gate and OR gate, we connect one inverter there. Now the answer to my first question, let me write it. My first question was, if I connect NMOS in parallel and PMOS in series, that was my question. Now, Vanilla told that will be an OR gate. No, OR gate also, it will be PMOS at the top, NMOS at the bottom. My question was a crazy question. You already know I am a crazy person. So I keep asking crazy questions. My question was like this. In the same circuit, let me replace PMOS with NMOS, NMOS with PMOS. What is this particular gate was my question. Now can any one of you answer this? Just look at this and try to answer this.
NOR gate, sir.
Which gate?
NOR.
NOR gate. So NOR gate, what is the output? Output will be 1 0 0 0, right? For NOR gate it is 1 0 0 0. We will verify. Here it is 0 0, NMOS is off, 0 0, PMOS is on. So output is 0. So obviously it is not NOR gate. It is not NOR gate.
OR gate, sir.
OR gate, OR gate output will be 0 1 1 1. So let us see 0 0, and here it is 0 0. 0 0, PMOS is on, output is 0. Now 0 1 0 1. Okay, 0 1, this NMOS is on. Now here it is 0 1. Now this is off. 0, this is 0, this is on, this is off. The lower switch is off. So output will be what? It will be Z. Output will be high impedance. Because if this is on, if it has to become 1, okay. Let me see whether I am hurrying up or not. 0 1, this is on, so this is 1. Now this is 0 1, 0 1, correct. This is now 1. Let us say it is 1 now. Next 1 0, 1 0, it is 1. Lastly 1 1, when it is 1 1, output is 1, and it is 0 0, output is now, sorry, 1 1, correct, output is 1. Now this is going to be OR gate. But I will tell you, this is not OR gate also. Tell me why. This is not OR gate also. Tell me why. I am trying to erase that. Can anyone tell me? No one is telling me. The answer is, as I told you earlier, PMOS cannot be at the bottom. NMOS cannot be at the top. Always PMOS has to be at the top. NMOS has to be at the bottom. Otherwise, we will have degraded output. So, even this circuit is not permitted. Fine. So, all other procedures are same. Just let me proceed. If there are no more questions, other things are, you will create a symbol. Just like you created the other symbol, you will create a symbol like this. NAND gate symbol you will create. You will connect to 2 pulses now. Because you need 2 inputs now. So, you will connect 2 pulses. Now, I will have one more crazy question. Now, you connect these 2 pulses. How will you give the conditions now as 0 0 and 0 1 and 1 0 and 1 1 to the NAND gate now, giving the input pulses. In the inverter, we had only a single pulse. We simply gave it. Now, when you want to simulate the NAND gate, How will you give these 4 conditions using these 2 input signals? Can anyone tell me? Basing on delay. So should we introduce delay here? Should we introduce delay? But we have not connected any delay here. See, we have simply connected 2 pulses. Okay, Kuldeep says by varying pulse width. Good, Kuldeep. By varying pulse width, which simply means that give different pulse widths for both of them. I will show you the output here now. See this. Here I can see one input is with this pulse, one input is with this pulse. That means you can see the pulse widths are different. So this is now 1, 1, then here now 1, 0, 0, 0, 0, 1. 4 conditions are there. So now you can see when it is 1, 1, output is 0. And when it is 1, 0, output is 1. 0, 0, output is 1. 0, 1, output is 1. Again, when it is 1, 1, output is 0. That way, you will have to vary the pulse widths of both of them. If at all you choose the double pulse width with each of them, let us say one pulse width you choose as 10 nanosecond, other pulse width you choose as 20 nanosecond, now automatically one will be double the other. So when they have that waveform, you will automatically get 0, 0, 0, 1, 1, 0, 1, 1. That is the output. Now my question here, just look at this. Why is this coming? And what is this called? Let me annotate this. Why is this coming? See? Why is this coming? And what is this called? Can anyone tell me? Okay, let me zoom, but I'll have to stop annotating now. Let me zoom. My question was this. Where did I go? Somewhere it went. Yeah, here it is. This was my question. Why is this? Why is this? This one. So Kuldeep says at same time one pulse going 0 to 1, other one going 1 to 0. Correct. At the same time you can see one pulse going 0 to 1, other one going 1 to 0. So there is a transition here. This is 0 to 1, 1 to 0. There is a rise time there. There is a rise time, there is a fall time. And whenever there is this particular overlap between transitions, you will get this waveform. But actually this is an unwanted waveform. This is an unwanted waveform, but we are inadvertently getting it. Now this waveform has got a particular name. What is it? Anybody? There is a particular name for this waveform. It is not occurring because of the levels, it is occurring because of the edges, because of the rise time and fall time, which are finite. So such waveform is called glitch. Remember this? This is called glitch. which is an unwanted waveform. We did not actually produce it, but it is part of the switching. Now in the digital circuitry, we will have to have glitch reduction circuits as well. Otherwise, these glitches may cause some erroneous outputs. We have to be careful about the glitches as well. So let me come back now. We have been discussing NAND gate. This is the NAND gate and this is the symbol and this is the simulation output. Similarly, we can have layout we will discuss later on in the next classes. Similarly, we can have NOR gate. You can see here, if you want to have a NOR gate, Pmos should be in series at the top and NMOS should be parallel at the bottom. Now this is NOR gate. You can verify this 0, 0, both Pmos are on. At that time NMOS are off. So output is 1. 0, 1, one Pmos will be off. At that time one NMOS will be on. So output will be 0. 1, 0 also same. 1, 1, both Pmos are off. Both NMOS are on. Output will be 0. So output will be 1, 0, 0, 0. Okay. So this is the NOR gate. So in static CMOS, we will not have AND gate and OR gate, because if we want to have AND gate and OR gate, we should connect NMOS at the top, PMOS at the bottom. That is not possible because of the degradation of the outputs. So what we do is, whenever we want to have an AND gate, we connect an inverter to NAND gate. Whenever we want to have an OR gate, we will connect an inverter to NOR gate. I am talking about only static CMOS. I am not talking of the other logic families. Okay, even the other logic families are there. All the other logic families have got their own issues also, their own problems also. That anyhow you are going to study in detail in the theory classes. Now this is the NOR gate symbol. Some of my colleagues or students have done a very nice NOR gate symbol where the NOR gate is really angry. It is upset. That's why I told you creating a symbol is basically an art. Now finally you simulate using the symbol and you will get the output like this. Now this is a NOR gate where you can see 0, 0 output is 0, 0, 1 output is 0 and 1, 1 output is 0, 0, 1 output is 0. Only when these are 0, 0 output is 1. This you can see. So this is the NOR gate simulation. In the next class, we will discuss the inverters layout. Later on, let me discuss the NAND gate and NOR gates layout. So, we have completed the second experiment now. Even though it was slow, I have a satisfaction that at least to my own knowledge, I have clarified your doubts, and to my own knowledge, I have given a basic description of the CMOS processes. So in the next class, let us start the inverter layout. You will have to remember all the layers and you will have to visualize always the N-well process. If there are no more questions, let me end the class. Are there any more questions?
So do we have to submit anything now in the Google Classroom?
Yeah. As I told you last time, you write one observation book for today's class and submit its PDF copy. Scan it and submit it. Even if it is 1 page also, 2 page also, it is fine.
Sir, observation book mein should we write all the steps to do because they are the same?
No need. You don't write the lab manual once again there. Whatever you have understood in today's class, that you make a note of it for your own sincerity. The purpose of writing observation book is that for helping you people to remember it. That's all. So only when you write, you will remember. If you don't write, it will simply evaporate. Unless you make an effort to recall, everything will evaporate. How I remember all these things? Because of the continuous teaching, I remember these things. Otherwise, even I will forget if I am not in touch with the subject. So to ensure that students are in touch with the subject, or if they remember whatever is happening, that is the reason of we asking you to write observation book. And for that only we give you marks there, right? Otherwise, you need not simply write whatever is there in the lab manual. You can sincerely make an attempt of writing whatever you learnt in today's class. But you can refer to lab manual. If at all you forget all that whatever is discussed, you can refer to lab manual also, and then you can write the observation book. Deepak will create one assignment in the Google class. Deepak, are you there?
Yes, sir. I have created, sir.
Yeah.
I have already created, sir.
Fine. Deepak has created an assignment in the Google class. You can submit all your observation PDF into that assignment. Okay. Shall we end the class?
Yes, sir.
Okay. See you then. See you in the next class. Until then, take
Thank you,
care.
sir.